So welcome to lecture 1 of chapter Electromagnetic Induction. So what do we mean to say when we say electromagnetic induction? From where does this idea originate? And from now onwards we will be referring it as EMI, that is electromagnetic induction. So in the previous chapters we have seen that the current produces a magnetic field. So now the question that was raised is there any possibility that a magnetic field can produce electric current? So now this question was first of all raised by Michael Faraday, and the answer to this problem is yes, that there is a possibility that by varying magnetic flux associated through a particular closed conducting coil, an electric current can be generated. So this phenomena in which electric current is generated by changing the magnetic field is known as electromagnetic induction, and the current so produced is called as induced current. So we can write it in the form of a statement: the phenomena in which electric current is generated, the phenomena in which electric current is generated by changing magnetic fields is known as electromagnetic induction, is known as electromagnetic induction, bracket में EMI, and the current so produced is called as induced current, and the current so produced is called as induced current. So basically, whenever I try to explain this phenomena of electromagnetic induction, we say that whenever there is a change in magnetic flux, whenever there is a change in magnetic flux associated with a conducting loop or a conducting coil, then an EMF, then a change in magnetic flux will produce an EMF induced, due to which the current is generated. We will discuss about it very soon. Now the phenomena of EMI is the basis behind the working of power generators, dynamos, transformers, etc. So it is the basis behind the working of generators, dynamos, transformers, etc. Generators, dynamos, transformers, etc. So the concept of EMI is responsible for the working of all these aspects. So we are beginning by understanding magnetic flux. So we understand the concept of magnetic flux. So previously we have read a bit about electric flux, and now we will be discussing about the magnetic flux. So magnetic flux through any surface held in a magnetic field is measured as the total number of magnetic field lines crossing the surface. So it is basically a measure of the magnetic field lines that are crossing the surface. So I am repeating one more time: magnetic flux through any surface that is held in a magnetic field is measured as the total number of magnetic field lines crossing the surface. So if we consider a surface like this, so we are considering a surface like this over here. So the area vector in this case is perpendicular to the plane. So this is considered as the direction of area vector for this particular surface that we are talking about. And we are considering that the magnetic field in this region is in this direction, that is B vector, directed vertically up, and the angle which B vector and A vector makes with each other is theta. So we can write from here that the mathematical formula for magnetic flux, the mathematical formulation for magnetic flux, that is equal to phi B, is equal to B dot A. So that is the mathematical formulation for magnetic flux, which we can write as magnitude B magnitude A cos theta. Just like any other dot product, we are writing it in this format, or we can also write it as B perpendicular into A. The flux can also be written as B perpendicular into A, where B perpendicular is basically B cos theta. So it is the component of magnetic field perpendicular to the face of the area. The direction of the area vector is normal to the face of the area. So B cos theta is in the direction of A vector, which we have marked in the figure. So over here, if I draw the direction of B cos theta, so this is the direction of B cos theta, that is in the direction of A itself. So B cos theta or B perpendicular into A can also be written as the value of magnetic flux. Now based on this formulation, we can write a small note. So if theta is equal to 0 degree, I'm extremely sorry, if theta is equal to 0 degree, then I mean to say that we are considering something like this, that there is a surface like this where the magnetic field is in this direction. So this is the direction of magnetic field, and area vector is in this direction. So the value of magnetic flux in this case will be simply written as magnitude B into magnitude A, where cos 0 is equal to 1, and this is the maximum value of magnetic flux. So this is the maximum value of magnetic flux. In the second case, I am taking if theta is equal to 90 degree. So if theta is equal to 90 degree, then we mean to say something like this, that we are considering this area. So the area vector is in this direction, and we consider that the magnetic field is directed in this direction. So this time if we calculate the value of magnetic flux, then it will be equal to B A cos 90, and the value will turn out to be 0. So magnitude B magnitude A cos 90, and the value will turn out to be 0 in this particular case. For the angle that is less than 90 degree, for angle of theta that is less than 90 degree, so the value of cos theta will be positive, and hence we write that the flux associated with the positive in this particular case. So we write it as positive flux. And if in case when theta is greater than 90 degree, then we say that the flux associated is negative. So we write it as negative flux in this particular case. So this is the basic idea about the value of magnetic flux. So now if we define magnetic flux through a small elemental area, in many cases we will define it in this way. So we are writing through a small elemental area, through a small elemental area. So if we consider a small elemental area and we define magnetic flux through that particular area, then I can say that d phi for that particular area will be equal to b perpendicular into dA. The total magnetic flux to the area is the sum of the contribution from the individual area element, and if we integrate this expression, then I can write it in this way that the value of this integral b perpendicular into dA will turn out to be the value of phi is equal to b cos phi or cos theta into dA, which we can write it as cyclic integral of b dot dA. So we can write it as cyclic integral we can write it as phi is equal to integration of b dot d. So this will give us the value of magnetic flux through a surface. Magnetic flux through a surface. So now we will be defining Faraday's laws of electromagnetic induction. So let us come to the statement of Faraday's laws of electromagnetic induction. Electromagnetic induction. So Faraday stated two laws about the electromagnetic induction, and it is regarded as the Faraday's laws. So the first one is stating whenever there is a change, whenever there is a relative motion between a magnet, that is a source of magnetic field, and a closed conducting loop, the electric current appears in the loop, and it is because of the change in magnetic flux associated with the loop. So we can basically write it as whenever there is a change in magnetic flux associated with a coil, an EMF is induced. Whenever there is a change in magnetic flux associated with a coil, then an EMF is induced. And the second one is the EMF induced, the magnitude of EMF induced is directly proportional to the rate of change of magnetic flux through the loop at that time. The magnitude of EMF induced, the magnitude of EMF induced is directly proportional to the rate of change of magnetic flux associated through a coil. So we write it in this way that the magnitude of EMF induced is proportional to d phi by dt, and then we write over here that the value of EMF induced is mathematically written as minus d phi by dt. So this is the mathematical definition which we write over here. The negative sign is attributed due to the Lenz law, because the Lenz law states that when the magnetic flux through a loop changes, a current is induced in the loop such that the it opposes the cause producing it. Basically, the statement of Lenz law can be stated as whenever the magnetic flux through a loop changes, a current is induced in the loop, such that the magnetic field due to the induced current opposes the change in the magnetic flux through the loop. So if we state Lenz law over here, Lenz law over here, so it states whenever the whenever the magnetic flux through a loop changes, a current is induced in the loop. A current is induced in the loop such that the magnetic field due to the induced current, the magnetic field due to the induced current opposes the change in magnetic flux through the loop. In magnetic flux through the loop. So this is the statement of Lenz law. So now whenever we will be applying Faraday's laws of electromagnetic induction, the direction will always be determined using Lenz law. We will calculate the magnitude using the Faraday's laws. That is, the EMF induced is proportional to the rate of change of magnetic flux associated with the coil, and the direction of the current induced will always be calculated or find using Lenz law. So if I write the statement one more time, the mathematical statement, so I write it in this way, that from Faraday's law, so we are stating it in this way, that phi is equal to B dot A, and when we are saying that the EMF induced, so the magnitude of EMF induced is equal to d phi by dt. So we can write it in this way, that the magnitude of EMF induced is equal to B dA by dt plus A dB by dt. So this can be consisting of the two parameters. So the magnitude of EMF induced can be written in this fashion, consisting of two parameters. So the EMF can be induced because of the changing area. So in the first part of the equation I am saying that B is kept constant, the area is changing. The area is changing with time, as in the case of the rotation of the armature coil in case of a AC generator, in which the area associated with the magnetic field is changing. The magnitude of magnetic field remains the same. Or it can be due to the second part of the equation, where we are saying that the area is kept constant. The area is kept constant. The value of magnetic field is changing or fluctuating. So the value of magnetic field is changed generally by establishing a relative motion between the coil associated and the bar magnet or the source of magnetic field. So if we establish a relative motion between them, then the magnetic field will change with time, that is dB by dt is produced. So these are the two parameters which must be kept in mind whenever we are writing the equation of EMF induced. So these two parameters generally contribute, one of them will become the reason for the contribution or the generation of induced EMF in the loop. And the direction of the current induced is always calculated or ascertained using Lenz law. So now we are applying the equations and the conditions which we have learnt about the electromagnetic induction and Lenz law in the following cases. So we are considering that this is a region of magnetic field where the magnetic field is directed into the plane of paper, something like this. So the magnetic field is directed into the plane of paper somewhat like this. And if we consider that the magnetic field is increasing, so when I say that magnetic field is increasing, then we mean to say that dV by dt is increasing or a positive value. So the magnetic field is increasing with time in this particular case. So over here I am drawing a loop like this. Suppose I consider three cases. So in the first one we are considering a loop like this, and in the second one we are considering a loop like this. And if such a loop is placed, we are asked to find out the direction of current in each of the loop. So if we consider the first loop, that is a circular loop which is placed in a magnetic field region where the magnetic field is increasing with time, so I can say that the magnetic field lines through the loop is increasing. And if the magnetic field lines through the loop is increasing, then the EMF will be induced in such a way that it will try to oppose the cause producing it, and the direction of induced current will be in the counterclockwise sense somewhat like this. So this will be the direction of I induced. So the induced current will be in this direction, that is, it will try to oppose the cause. So as the magnetic field is increasing into the plane of paper of the ring, so it will try to produce the current in the counterclockwise direction so as to oppose the increasing strength of magnetic field. We can also consider this in this particular fashion. If I draw another diagram, suppose we have a conducting ring like this, and I am bringing a north pole of a magnet towards it. So if we are bringing the north pole of the magnet towards this particular coil, so then what is happening is the magnetic field lines associated with this particular coil is increasing. So it will oppose the cause producing it. So in order to oppose the cause producing it, it will produce a north polarity. That is, the current will be flowing in the counterclockwise sense. So it can be asked in this way as well, or can be understood in this way as well, that if the magnetic field is increasing, so we mean to say that if a bar magnet is moved towards the coil, then the current will be induced in the counterclockwise sense so as to oppose the cause producing it. Because if we are taking the north pole of this magnet towards the coil, so the number of magnetic field lines associated with it will also increase, because the north pole will produce the magnetic field lines directed away from it. So the direction of the current induced must be in such a way that the coil will produce the magnetic field line that is directed away from it, and hence the current is induced in the counterclockwise sense in this particular coil. If we take another example over here, so in this case a closed coil is placed which is having an inner and outer radius, and now it is placed in a magnetic field which is increasing with time. So the direction of current will be determined by the outer loop. So when I say by the outer loop, it is because of the fact that the more change in flux is produced due to the outer loop because of its larger area. Because of its larger area, the outer loop will produce more flux because of its larger area in comparison to the loop which is inside, and hence the direction of current is determined by the loop which is the outer loop. So in this case the direction of current is as marked in this particular diagram over here, that is, in the outer loop it is in the counterclockwise sense, and in the inner loop it is in the clockwise sense. If we take a similar example over here again, so we can take an example like this in which the magnetic field is directed into the plane of paper. The magnetic field lines is directed into the plane of paper, and we are introducing or removing a particular coil. So in this we are considering, suppose we are bringing in a rectangular loop like this. So we are naming the sides as A, B, C, D, and this loop is being introduced into the region of magnetic field, And on the other end we are taking another one where I am taking a triangular loop and we will be taking it outside the magnetic field and we are naming its side as ABC again. So if we consider this particular case, then in the first case in which we are taking a rectangular loop ABCD, the magnetic flux to the rectangular loop will increase. Why? Because the magnetic field line through the loop will increase because of the introducing more area into the magnetic field. So the magnetic flux is increasing when the loop is introduced into the region of magnetic field. So now the direction of the induced current will be such so as to oppose the increasing flux. So in order to oppose the increasing flux, the direction of magnetic field induction or the induced current will be in the direction BCDAB. I am repeating one more time. As this rectangular loop is coming into the region of magnetic field B, the more area is coming into the region of magnetic field and hence I can say that the magnetic flux is increasing. So in order to oppose the increasing flux, the direction of current is in the counterclockwise sense so as to oppose the cause of increasing magnetic flux. Now in the second case when we are taking a triangular loop and it is taken outside the magnetic field region. So I say due to the outward motion, the magnetic flux through the triangular loop is decreasing because the number of magnetic field lines associated with this triangular loop will go on decreasing and hence the direction of current will be so as to increase the value of magnetic flux through this coil and hence the direction of current will be in the clockwise sense, that is from B to A to C to B. That is, as this loop is coming out of the region of magnetic field, as this loop is coming out of the region of magnetic field, the current will be induced in such a way that the direction of current will be in the clockwise sense or from A to C to B to A again. So these are the examples that are associated with the direction of current induced using Lenz law. Now we are taking a numerical example. So the problem is stating a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, then what is the induced EMF in the loop while the current is changing? So if we are taking the number of turns over here, it is stating the number of turns on the solenoid is 15 turns per centimeter. So if we convert it into meter, it will be 1500 turns per meter. The next fact which the question is stating is the solenoid has a small loop of area 2 centimeter square. So the area of the loop which it is talking about is 2 centimeter square. So we can convert it into meter, that is 2 into 10 to the power minus 4 meter square. And now the value of current is changing from 2 ampere to 4 ampere. So I am writing I1 is equal to 2 ampere and I2 is equal to 4 ampere. So the change in current is 2 ampere taking place and the time taken during this change of current is given to us as 0.1 second. So if I write the value of magnetic field due to a solenoid, then the magnetic field due to a solenoid B is equal to mu naught Ni. And the coil about which we are talking about the flux change, then if we write the value of flux, so we are writing it as mu naught Ni multiplied by area A. So the change in flux will produce the EMF induced and hence the value of EMF induced can be written as, the magnitude of EMF induced can be written as d phi by dt. So now in this case when we are talking about d phi by dt, so we are talking about the current change that is taking place because all the other parameter remains constant. So all the other parameter is remaining constant. We are talking only about the current change with time. So di by dt will give us the value of EMF induced, and if we are calculating the average EMF induced, so I can write over here, therefore the average EMF induced, so the average EMF induced can be written as mu naught into area, that is 2 into 10 to the power minus 4 meters square, into small n, so we are taking it as 1500 turn per meter. Now the value of change in current over here, that we write delta I by delta t, so it is 2 ampere in a time duration of 0.1 second. So this is the value which we are talking about. So this is the value which we are talking about, and if we put mu naught as 4 pi into 10 to the power minus 7, so we attain a value equal to 7.54 into 10 to the power minus 6 volt. So 7.54 into 10 to the power of minus 6 volt is the value of average EMF induced associated with this particular loop which the problem is talking about.